Hello, good morning to everyone. I'm going to tell you a story about bears, about the beak of the bears, seeds, and mathematical models in order to understand a little more how evolution works. First of all, we have to imagine that a couple of bears arrive to an island where there are no other bears. However, in the island, there are many seeds. Some of them are big, some are small, and we can imagine that most of them have a mid-size. There is an important relation between the seeds and the bears, that is that big bears, bears with a big beak, can eat only large seeds, while bears with tiny beaks can eat only small seeds. Taking this ecological relation into account, we wonder how evolution will work on the bears. It can happen that the beak of the bears will evolve toward an optimal size that allows the bear to eat as much seeds as possible. Another thing that it can happen is that once the bear has arrived to this optimal beak, because there is a lot of competition between the bears, then it is better for the bear to change a little the beak in order to explode another kind of seeds, the bigger or the smaller. And if this happens, we have a branching process that splits the original species in two. In order to decide between the first or the second scenario, we are going to modelize the problem. First of all, we are considering only one population. This is the resident population, and we can modelize the ecological system by the classical logistic equation. Here, we are supposing that the bear has a beak of size x, and k of x is the carrying capacity of the system, of the population of bears. K of x is related with the amount of seeds that the bear can eat. It is easy to see that the population tends to an equilibrium that is exactly the carrying capacity. So if a mutation occurs, and mutation occurs rarely, we can suppose that the population is on its equilibrium when this happens, and we want to know what will happen next. To do this, we modelize a more complex system with two differential equations, and because the phenotypes of the mutant and the resident population can be quite similar, we introduce a function that gives us the competition between the mutant and the resident population. With that, there is a formalism that allows us to respond important questions such as, does the mutant can invite and replace the original population? If this happens, then there is evolution in the best population because there is a change in phenotype. There is a mathematical formalism, quite complex, that allows us to study this. And it can be shown that depending on the variance between the carrying capacity and the competence, we will have one scenario or another. In fact, if the competition doesn't change a lot, if we change phenotype, then there is no need to change phenotype. While if changing a little the phenotype, the competence is reduced a lot, then we will change phenotype and we will have the branching. There are many questions related to that problem, like the first one is that bears are sexual populations, and so phenotypes can be mixed, and this is a problem. Then what happens with polymorphic populations, and these kind of things is the ones I'm working in. Thank you for your attention, and my partners, the CRM, is where I work. Thank you very much.